Hello, good morning, everyone. You have an interesting talk, friends and family. Okay, so we meant to start this class by 10 a.m., but no one joined. So I decided to record the section and then I'm going to upload this on things and to watch. And then maybe we're going to back to something to take on. Okay, so we're just trying to finish up the topic early on, and then we can start the class in January. Okay, so I'll go straight into what all we have for today, and the topic is introduction to organic chemistry. Of course, it covers some aspects of this topic. So I'll be focusing on three main highlights today. Okay, so let me share my screen so that you can see what our focus is going to be on today. Okay, I think I'm sharing the screen already. Okay, so the topic is organic chemistry. So the lemon organic compound, we're talking about isomerism and reaction mechanism. Okay, so if you're able to complete this, then move on to something else tomorrow. Otherwise, continue with this tomorrow. Okay, so of course, I've said this, the learning focus is learning of organic compounds, talking about isomerism and reaction mechanism. So let's start by introducing the functional group. Okay, so functional group, of course, is the active site of an organic compound. Okay, the site that determines the chemical properties of the organic compound. So it contains atoms, or let me use the word molecule, okay, that determines the chemical reaction or the chemical characteristics of the organic compound. That is what the functional group is. Now, there is this general formula that can be used to identify organic compounds based on the functional group. So I have the formula summarized this way. So I have RH for alkane, RH, where R here stands for the alkyl group. Okay, the alkyl group, this is general formula for the alkyl group. R is CnH2n plus 1. For example, if you have one carbon, okay, the alkyl group for single carbon will be C1H2 plus 1. Okay, so that's will be CH3. So this alkyl group here is called methyl. Okay, then you can have the next one, C2, C2. If you multiply 2 by 2, that will be 4 plus 1, that's 5. So the second member of the alkyl group is uh, methyl. Okay, now check each of these alkyl CnH2n plus 1. That's general formula once again. If I add one more hydrogen to this alkyl group, what you come up with will be CnH2n plus 2, which is the general formula for alkane. Hence, the general formula based on the alkane functional group is RH. Okay, so you have the alkyl group plus one hydrogen. That is alkane. Okay, now moving on to the next one is the alkene group. The alkene group has the alkyl group, and then you have an halogen attached to that alkyl. Of course, halogen are all elements in itself, so it can be any of these. It can be fluorine, it can be chlorine, it can be bromine, it can be iodine. Okay, so any of these halogen X represents any of the halogens, fluorine, chlorine, bromine, or iodine. So when you have an alkyl group with an halogen group attached to it instead of hydrogen, or you have the hydrogen of the alkane substituted with an halogen, you call that halogenoalkane. That is the functional group. Okay, so you call that functional group halogenoalkane. Okay, now still on the alkane group, if I remove the hydrogen ion or the hydrogen atom, sorry, of the alkane group and then I replace with an OH, I form another functional group, which is the alcohols. Okay, so when you replace the hydrogen of the alkane group with OH group, you form a functional group alcohol. And of course, the alcohol group have a different chemical property from the alkanes or the alkane. So you can see these are the functional group. Those things are attaching to the alkane determine the functional group of the compound. Okay, or determines the nature of reaction or the characteristic of chemical reaction of the compound of the organic compound. So you have this for for alkanol, sorry, alcohol or alkanol. Now I have the word alkanol here because you can name alcohol in different ways. This is the general name alcohol, general name for all functional groups in this formula. But if you want to be specific, systematic name for all those alcohol is called alkanol from the word alkane. Okay, so the corresponding alkane will determine the name of the alcohol. Let's see one or two examples before we move on. Okay, so I'll just show you one or two examples. So we're going to look at one or two alkanes and then we'll see how we can derive an alcohol or alkanol group from it. Okay, so let's start with methane or methane. Okay, so methane is CH4. If I'm going to write it in this form, it should be CH3 with one hydrogen, this methane. Okay. Now replacing this hydrogen with an OH group, I'll have CH3OH. This way, CH3, then you have your OH. So if this is methane, then what will be the name of this compound? Following the systematic name from alkane, methane, okay, just replace the N with OL. So this is going to be methanol. You are replacing the ANE of the alcohol with just OL, okay, or the NE of the alcohol with OL. Then you have your alkanol. Okay, so that's it. So that's just the way systematic name and specific name works. Okay, so specific name is the general name for all the alcohols. But if you want to be more specific, use the systematic name for the alcohol. Okay, for example, methanol is a more specific name, or I'll call it a systematic name for a certain alcohol or for a certain alkanol, okay, with one carbon. Let's see another example. C2H6. This is methane. Sorry, this is methane. Sorry. This is ethane. Uh, that's the alkane group. So this is ethane. So I can replace the last hydrogen there, making it C2H5. So plus one hydrogen and then replace it with OH. Systematically, I'm going to use the same alkane naming. So it's going to be SR. Then I'll replace the E with OL. So I have ethanol. So systematic names help us to name the organic compound better rather than using the general name. Okay, so the general names can actually be confusing, but if you're able to get the systematic name, you can draw the structure, you can write the molecular formula, you can write the structural formula easily. Okay, using the systematic name. So that's why I also try to include the general systematic name for some of these organic compounds in this slide, or let me say in this presentation. Okay, so for alcohol, you have them as alkanol, that's your systematic name. The next group I have here is the carboxylic acid group. So the carboxylic acid group has the functional group COOH. The same thing is happening if you check all of them. You can see that the hydrogen atom of the alkane is being replaced with a functional group. Here is replaced with OH, here is replaced with an halogen, here is replaced with COOH for carboxylic acid. So the systematic names still follow the same format, or let me say the same procedure. Okay, so for carboxylic acid, I can call them alkanoic acids. So from the alkane, then you just change to oil. You just add oil to the E, I think that to the E that ends the alkane. Okay, so replace the E with OIC, oil. So call them alkanoic acid. Okay, so the next one I have there is esters. Okay, and the systematic name for esters is alkyl alkanoids. Now let's try to make sense out of this. Okay, let's try to make sense out of this. Alkyl alkanoids in the sense that, let's see, the formula is RCOOR. Now you can see this R here is carrying something like a prime. Okay, so showing that this R here can or might be different from the first R. The first alkyl group and the last alkyl might not be the same. So I'm going to see different example where you have the same alkyl group, okay, as the first one, and then the same alkyl group for the functional group. Or you have different alkyl groups in the general group and then different alkyl group in the functional group. So let's see example. So I can have CH3, for example, COO, then CH3. Now I want to name this alcohol using, sorry, ester, okay, using the systematic name alkyl alkanoid. So how do I name that? I'll start the naming from the very first one. So what do you call this? What will you call this alkyl group? This is methyl, right? This is methyl or methyl group, okay? And then the next one I have just CH3, okay? Now the next one I have two carbon. I have one here, I have another one here. So I have to pour the two, or I have to add the remaining carbons together, okay? So for the second one, or for the second part of the name, which is the OH part, I have two carbon there. So for two carbon, I think that should be an S. Okay, so I'm just going to write it as oh sorry, sorry. So this is the systematic link. So from methyl, then two carbon, that's that is ester, then you replace the E with OH, OAT, OAT. So I have methyl ethanoate for this compound. Okay, so that is the name. All right, so check that again. You can try to name as many as possible. Then you have the ester group, the ethyl group rather, or the alkoxy alkane group. You have the ketone group, which is the RCOR, COR prime. You have the aldehyde and alkoxide group. You have the amine. You have the amino acid. Our focus is actually not on all of these. Our focus is only going to be on the first three, yeah, the first three, okay, for paper one. Okay, so I'm going to just take a break on that now and then move on to the next slide. Okay, before I talk about isomeric. Okay, so the next thing I'll be talking about naming of organic compounds. How can we name, or how do you name organic compounds? So the naming of organic compounds follows from certain rules. If you are able to follow this rule or understand this rule, it's easy to name any organic compound. Or it will be easy to name any organic compound you might come across at all. Okay, so just following those certain rules, you will be able to name any organic compound successfully. Okay, so don't forget, I told you at the beginning of our chemistry lesson, you don't need to cram anything. All you just need to do is to understand the principles, understand the rules, and then apply them appropriately, apply them the right way you should apply them. Okay, so now let's go through the rules and then we're going to name an organic compound together. I have an organic compound written here. Let me see. I think I have an organic compound. Okay, okay, great. So we're going to name this organic compound afterwards. Let me write the structure. I just came across it on online, so I think it's interesting to just use the rule to name the organic compound. Let me draw the organic compound first, so we're going to name this organic compound afterwards. One, two, three, four, four. Then you have the fifth one, consists of two carbon atoms, okay, across this, and then have a chlorine here. You have a bromine attached here. You have another bromine attached here. And of course, every other thing that are hydrogen. So these are all hydrogen. So we're going to name this compound, okay, following the set of rules we have laid down, the set of rules I have in this slide. Okay. Okay, so that's the organic compound. See if I can change the color for so something deeper. Okay, so, yes, that's good. All right, so now rules for naming organic compound. Number one, the first thing you want to do is to identify the functional group in the organic compound or the position of the side chain. Now, let me explain what this means. In some organic compounds, especially alkanes, you don't have functional group. You can have branches of alkyl group, okay? So the branches of alkyl group are the position side chains, okay? Or those are the side chains. So you can have side chains, okay, that branches of the main chain, the main carbon-to-carbon chain of an organic compound, especially in alkane. Let me show you an example. I have this alkane here. You see no functional group. I have C here, maybe I have another C here, another C here. Okay, okay, so this is hydrogen, this is hydrogen, let me just write this as CH3, hydrogen, CH2, this is CH3, okay, and these are hydrogen atoms, and of course, okay, so now look at this compound, for example, now. There is no functional group. You don't have an OH group, you don't have a COOH group, you don't have even an halogen group. You don't have any of those common functional group here. Okay, so in this case now, when you don't have a functional group, what you have are the side chain. So these are side chain. This is a side chain, for example. This is another side chain. Okay, because you can see them, they are bearing off the main connecting the straight. Did I use the word? Yes, the straight line carbon to carbon bond. Okay, so it's bearing off the chain. Okay, so it's bearing off the straight chain. You get that? So you call those one the side chain. Okay, so uh, I'll read I'll read that instruction again. So that's first rule again. It says identify the functional group in the carbon to carbon. In, identify the functional group in the compound or the position of the side chain. So in this case now I have side chain. In the other one, in the other example, I have functional group. So let's do the same thing for the two of them. We want to identify the functional group or the side to side carbon. So in the first one, I've identified the side to side. Let me show you again what the side to side carbon atoms are, where the side to side group, where the side chain group are. So I have CH3 here. This is the side chain color. So this is side chain group one. This is another side chain two. So I'm still going to talk to you more about the side chain group, okay? I'm still going to talk more about that. Now, when you have a side chain, okay, let me read the next one and then I'll talk, maybe I'll still talk on what I want to talk about again. So now I've identified the side chain group here. I have two side chain groups. I have one up here, then I have the second. For this one, I have a side chain group, which of course would have been this. Then I also have the functional group. In situation where you have the two, okay, what takes precedence will be your functional group. I'll say that again. When you have a side chain group and a functional group mixed together in an organic compound, what takes priority for your naming of for the naming of the organic compound will be the functional group, not the side chain group. In this case now we have only side chain group, no functional group. So the side chain group is what we're going to use to determine the numbering of our carbon. But in this case now, we have a functional group and then we also have a side chain. Okay, so what takes precedence or what determines the naming of a compound here will be the functional group or the numbering of a carbon atom. What will determine that will be the functional group, not the side chain. Clear with that? Okay, now I'm going to rule number two. Rule number two says number the carbon atom starting from the carbon end closest to the functional group or side chain. Identify the longest carbon-carbon chain to determine the alkane base. Good. Let me break this down. So I'll follow the punctuation mark. It says number the carbon atoms. How do we need to number it? You need to start from the carbon that is closest to the functional group or the side chain. So let's try to do that. So let's first of all identify our carbon ends. Okay, let's first identify our carbon ends in the compound. For the first compound, I have this carbon here. This is a carbon end. This here is not a carbon end because it's a functional group. So I think the second carbon end is actually here. So I have two carbon ends, this side and this side. These are my carbon ends. This is a functional group, not a carbon end. So please take note of that. So I have two carbon ends. So starting from now, I have two carbon ends. It's confusing. Which of these carbon ends can I start my numbering from? Now you now have a further instruction there that says starting from carbon end closest to the functional group. So now let's check which of these two carbon ends is closest to this functional group. These are functional. So which of the two carbon ends, this one or this one, which of these two is closer or is the closest to the functional group? So let's start numbering from here first. So if this is the first carbon end, 1, this is going to be the second one, 2. This is going to be the third one, 3, 4, 5, 6. Okay. Now, if I'm numbering starting from this other carbon end, then I should have 1 here. This is 2, this is 3, this is 4, this is 5, and this is 6. Now, based on your numbering, okay, based on your numbering, which of these two is closest to the carbon end, is closest to the functional group? Is it the carbon 4 or the carbon 3? Of course, the carbon 3 is closest to functional group, meaning if we are going to number, we need to start from this carbon end, the one at the base carbon end, not the one on the far left, or the one on the right, okay, that is base to that. Okay, sorry, I'm going to redraw this, don't worry. I'm going to write all that. That's right. Okay, so let me write this. Yeah, carbon here. Carbon to iodine. Okay, so that's what I have there. All right, so I have that. Then I've numbered them starting from the carbon that is closest. Okay, so I said the closest carbon is numbering this with 1, 2, and 3. So I'm following this numbering system that goes this way. Okay, so this is going to be my longest carbon to carbon chain, not carbon to carbon straight chain. Please take note of that. Okay, we're not looking at carbon to carbon straight chain. Straight chain can be like this or slant or maybe vertical. No, I'm not looking at carbon to carbon straight chain. It's just carbon to carbon chain. Okay, so the carbon to carbon chain can actually branch off. But as long as it is continuous carbon to carbon chain, then we can use it. Okay, so this is a continuous carbon to carbon chain that I have identified there already. Okay, successfully. So I'm going to use that carbon to carbon chain. Now let's look at the second example. Let's identify we've identified side chains. Okay, you have the C2, CH2, and then the CH3, and then the second one you have a CH3. So now we need the longest carbon to carbon chain. Don't forget, okay? Now, if you have the longest carbon to carbon chain, then the next one, the other one definitely is going to be like a side branch to that carbon to carbon chain. So let's check our carbon to carbon chain, how it connects. So you have a carbon here connected to another carbon. So first carbon to carbon chain, second one, third one, okay, fourth, then this is fifth, this is sixth. Then I can check this way as well. One, two, three. Okay, apart from this, I think there is none again. So if I'm going to check my carbon to carbon chain, I have this one, I have this two, I have this three, the carbon to connect four, and then five. So meaning this one that goes up here is not a side branch of the carbon because it's the longest carbon to carbon chain. So there is only one side branch of this or for this organic compound, which is this, the CH3. So this is the only side branch in this organic compound. Okay, so I've identified, I was having issues identifying my side branch here. I thought there are two side branches, but I can see clearly now that the other one, the one at the top, is actually not a side branch. So you have to be careful of those pitfalls, okay? Be careful of pitfalls like that when you're identifying your side branch. The first thing you want to do is try to mark them out first and then trace your carbon to carbon chain. Check the one that is the longest, okay? Connecting carbon to carbon chain and then start removing some that are not side branch, okay? And then you can know how many side branches you actually have, okay? So the next thing we want to do now is start with the number of, it says number the carbon. Okay, so I've not numbered this carbon atom. So I have already. So I have one, two, three, four, five. So I have the carbon atoms there. Okay, so I'm going on to the next step now. It says start with the number, name, starting with the number, name the branch molecule or atom alphabet in alphabetical order. Okay, so we have to name the branch molecule in alphabetical order. So this is the branch molecule here. CH3. In this case now, is there any branch molecule? No, there is no. Oh, there are branch molecules there. There are branch atoms there. You have a chlorine, you have bromine, you have, oh, this is another BR. This is a bromine. Let me correct that. Not a bromine. This is going to be a bromine. So we have branch molecules. So the first, let me first identify my branch molecules, and then it will be easy for me uh, to number them. Okay. So these are my branch molecules. Okay. So for this one, I have one, two, three branch molecules apart from my functional group. For this one, I have just one branch molecule. Okay, and that's the functional group more or less because there is no functional group in alkane. Because alkane all hydrogen. So okay, so that's what I have. Now, what do I need to do next? Okay, so next thing to do is I've la- um I've counted the number the carbon atom, so I need to name the branch molecule in alphabetical order. In this case, now I have just one branch molecule, which is methyl. Okay, so the name of this methyl, or with the number, okay, with the carbon atom position in this methyl, I have one, two, three. So the methyl is in the top group. I'll say this three methyl. Okay, then the longest, the last thing is name the base alkane with the functional group. So in this case now, my base alkane is the longest carbon to carbon. One, two, three, four, five, six. So this is 18. So 3-methyl 18. So I'm done naming this one. Okay, I'm done naming this. One. Sorry, yeah, yeah, yeah. Forms, form, I think I'll just put that. Okay, sorry about that. Sorry for distraction. where I am. Okay, so now I've named this one successfully. So this is 3-methyl, okay? Hexane. Let me show you again how I named this, okay? Following the rules, okay, for naming organic compound, the rules we have up there. Okay, so I just follow the simple rules and then I was able to name this compound. So the first thing is to identify the functional group. In this case, there is a functional group. I name the carbon atom starting with the carbon and closest to the functional group or side chain. Identify the longest carbon. So my side chain in this case is uh this is the side chain. I have only one side chain. So numbering the carbon atom, I have 1, 2, 3, 4, 5, 6. Okay. So if I'm to number from this end as well, I have 1, 2, 3, 4, 5, 6. So if I'm numbering from this one, if I start my number from this one, this is not the closest. This the side chain here, this is not the closest carbon atom to the side chain, okay, because the side chain now is going to be on carbon number 4. But if I start counting from here, the side chain is going to be on carbon number 3, okay, so that means this carbon atom here is, of course, the closest carbon atom to the side chain, okay. So this is the side chain here, closest carbon atom to the side chain. So that was the first, that was the next to my key. Then I number the carbon atom. So I have 1, 2, 3, 4, 5, 6. So the side chain is on the third carbon. So I name it 3-methyl. Okay, it's on the third carbon. Position is 3. And then what is the side chain I have there is methyl. Okay, then the longest carbon atom, carbon to carbon atom, is 6. So that's the base name is hexane. So that's how I name that. Now, going to the next one, the one I actually wanted us to think. So following the same rules, the same set of rules today. Okay, I think I will erase this. I'll try to restore it, okay, reduce it in order to make it neater, and then we will be able to understand it or appreciate it better. And I think I'll also be using a different color of marker to draw it this time around. So let me use black. Okay, so using black, let me draw it. I have it here. So I have the carbon, oh, black, come on. This is made good. Good is not appearing the way I want. Oh, so you have carbon, with A, let me try to see them down a bit. I have no space there. C, C, C. How many? Oh, four. Wait, four. Then you have C, O, O, H. Then on the fourth one, I have two carbon attached. So let me just write this as actually. I think makes it easier that way. For this one, I have chlorine. On this one, I have bromine, and the other hand side. Then on this one, I have another chlorine again, and then you have the other hand side again. And of course, this is this. Okay, so now I want to name this using the same method, same rule, okay, for naming organic compounds. The same set of rules we have there. Nothing is changing, exact same thing. So we have identified a functional group. This is a functional group. So the functional group is the oil carboxylic acid. Okay. Now the next thing is to determine my longest carbon to carbon chain and then check which of the carbon end is closer or the closest to the functional group. Here is my functional group. I have two carbon ends. I have this end, then I also have this end. So which of them is closest to this functional group? Of course, this one. So I'm going to start numbering from here. This is carbon number 1, this is carbon number 2, This is carbon number 3, this is number 4, this is number 5, and this is the 6th carbon. Okay, so I have my carbon to carbon chain, longest. You have 6 of them. Now, the next thing is now to identify my side chain and the position of my functional group. So, the position of my functional group, okay, I think I'll do that last. Let me start with the position of my side chain. So, I have a fluorine on 3, so you have 3 fluorine somewhere. Then you have bromine on carbon number 4, so you have 4 bromo. Then you have another fluorine again on carbon number 5, so you have 2 fluorine basically, okay? So because I have 2 chlorine, that should be difluoro, okay? 2 means di, okay? So I have 2 chlorine, so I can call that difluoro, but I have to identify, or I have to point out the position of each of the chlorine atoms. So, but don't forget, I have to do this thing in alphabetical order. Okay, so let me start now. I have everything I need. I have, let me write them out, okay, so I can put them together when I'm done writing them all out in different space. So I have 2 fluorine, you have 1 on 3 Cl, you have another one on 5 Cl, then I have a bromine on 4 Cr. Also, my functional group, I need to also identify the position. My functional group is also on the fourth carbon, so 3CO. H. Okay, so I have the position of all the side chains, including the functional group. And I know the longest chain is the, what do you call it? 6 carbon, okay? That's hexane, okay? And then the functional group is carboxylic acid. So let me start alphabetical order. Of course, I need to name my side first. So my side chain are 4 in alphabetical order, 4 bromo, which is this. Then I have my fluoro, 3 and 5. So I'll say this is 3, 5 fluoro. Then what else do I have? Oh, I think that is all the side chains. Okay, so now the name is hexane. So you have what's going on? What's increased that value by doing that? It's something wrong somewhere. Uh, Okay, so I had a fluoro here. Don't worry, I'll just continue with that. So I have oh, it's not just fluoro, it's dichloro. Okay, I have 2 fluorine. So it's not just 3,5 fluoro, it's 3,5 difluoro. Okay, difluoro because there are 2 fluorine there. Then I have hexane. Hexa. Now I have to pause here because my carboxylic acid, the functional group is not on the first carbon atom. I have to indicate the position. So it's hexa. 3 is for the third carbon atom, oil acid. Okay, so the name of this compound is 4-bromo 3,5 dichloro hexa 3-oic acid. So that's it. That's how to name the organic compound. So I think we've achieved that thing. That's what we want to learn there, naming organic compounds. So you can try to practice as many as possible. Try to name as many as possible organic compounds. Just follow the same rule, the same set of rules I have there. Okay, or I've shown you there. Okay, so I think the next thing I want to talk about now is isomerism. Okay, so the next thing I'll be talking about now is isomerism, and then I'll focus on what is required, okay, for paper one. Okay, that is unit one of your syllabus. Okay, so in unit one of the syllabus, it makes you understand chain isomerism and position isomerism. Of course, there are other forms of isomerism that we'll be talking more about in Unit 2, functional group isomerism, stereoisomerism. Okay, but for now, our focus is not going to be on any of those two, other than the first two I highlighted of the chain isomerism and positional isomerism. Okay, so 1 minute, 1 minute. Okay, so first of all, let's define what isomerism is. What is isomerism? So isomerism is just a phenomenon which describes the nature of an organic compound that has the same molecular formula to exist in different structural form. Okay, you can say they have different structural formula. The same molecular formula, but they can exist in different structural form or they have different structural formula. Hence, the name of the compound will be different. Okay, the molecular formula is the same, but the name of the compound is not the same. Okay, it can form different compounds, so to speak, because it has compound with different kind of names. So you can say the organic compound forms a different compound. So I'll talk about this more extensively when we check examples. Okay, so now there are two types. Oh, sorry, there are four types of isomerism. The first one is the chain isomerism. The next one is the positional isomerism. We have the functional group isomerism, and then we have the stereo isomerism. So, like I said, focus is on the first two. So I'll start with chain isomerism. Now, in chain isomerism, what makes the difference is the side branch of the organic compound. The side branch takes different positions, but you have in total equal amounts of carbon, equal amounts of hydrogen, equal amounts of oxygen, equal amounts of chlorine in the compound, depending on how many atoms it contains. Let's look at the example. Let's look at this example. Let's say C4H9Cl. Okay. So look at this. So in this, oh no, let's just do normal change. Let me not, I don't want to include position yet. Okay. So I'll just do only change. All right. So C4H8, C4H8. Let me not mix two together. So C4H8, okay? So I'm looking at only chain isomerism here now, okay? So now let's see how the chain isomerism thing works. So you have C4H10. If I'm to draw this organic compound, I can have four carbon atoms attached to each other this way, connected this way, okay? So you have all the hydrogen atoms as well connected this way. If you count the hydrogen, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so that's it. This is straight chain isomer. Now I can break the first carbon atom, okay, away and then change the position. Break it away and then make it a side chain in this compound. Reduce the number of carbon connections, direct connections 3, and then place the first one, this very one, okay, bring it down here. So it becomes a branch. It becomes a side branch in the main chain. But the thingy is still the same. It's still the same. If you count the carbon is still 4. You still have 1, 2, 3, 4 carbon. Okay. Count the hydrogen. You realize that you still have 10. 3 plus 3, that is 6 plus another 3, that is 9 plus 1, that is 10. Still the same C4H10. But what has changed? You have this one on a straight line, you have this one straight line, and then one of them is branching off. One side branch, okay? So this is a chain isomer. The chains are not the same. Now, I said because of that, because the structural formula is not the same, they will have different names. Let's see how this is. What is the name of this? This is butane. Straight up, this is just butane. 1, 2, 3, 4 carbon with all the hydrogen attached to it directly. Okay, so this is butane. What is the name of this one? Now, to name this one, you have to follow the systems of naming. But because you don't just have the stem name, or let me say the base carbon to carbon atom name, or the base alkane name alone, you have a side branch. Okay, so that makes the name different. So let's see, how do we name this? You have 1, 2, 3 carbons. Okay, those are side to side. You can also name it, you can also cancel this 1, 2, you can cancel this way. So either way, either you're counting it down like this or you're counting it straight, you still have 3 carbons as the longest carbon-to-carbon chain. And either you're counting it straight or you're counting it down the other way around, you still have your side chain to be on the second carbon atom. So either way, so it's just okay for me to probably leave it this way. So this is my side branch carbon. Okay, so the straight chain carbon or the longest carbon to carbon chain is 1, 2, 3 carbon. That is a propane. Then you have a methyl group in the second carbon. So this is two methyl or methyl propane. So look at that. Same molecular formula, different structural formula, different things. So if you are asked to define isomerism in a way, and then probably the your definition is meant to carry too much. So please try other things. These are other things that you can include to your definition. Number one, they have the same molecular formula, different structural formula, hence different name for the organic compound form. Same molecular formula, different structural, and then different names. You want to get full definition or full map for your definition, I think it's better to define your isomers that way. Okay, so I'll move on to the next one, which is positional isomerism or positional isomer. So now in positional isomer, it's not just a side branch you have a functional group that has a different position in the organic compound. Okay, I think I have some examples. Okay, so I'm going to use the examples I have up here as, okay, let me go back to this one because I'm just explaining that only what I have on the next slide, like a kind of activity. So I'm going to just have to. So let me play this. Okay, so now the same organic compound, what I'm going to do is to just change the functional group by replacing the one or two of the hydrogen atom, replace it with a different functional group. Okay, let me just take this out. I'll take that off. So still the same number of carbons. So C4 instead of H10, let me replace two hydrogen there. Let me make it H8 and then replace with one bromine and then one chlorine. Okay, so you have C4H8Cr. Okay, so now I'm going to draw the position, the isomers for this. So of course I know, well, a lot is going to go. Can I reduce this? Myself again. All right, so let's see. Let's try to draw the isomers for this. So you have four carbon atoms, straight. Okay, you have the branching. You have bromine and fluorine. You can have them on the same carbon atom at first. This is position. Okay, they are both on the fourth position of carbon. They are both on the fourth carbon atom, bromine and fluorine. I can also redraw this or rewrite this and have them on different carbon atoms, fluorine here, to, oh, to be on the second. I don't want to just jump, okay? Okay, the fluorine there, yes, they need here. Okay, so you can see one is taking the position of the first carbon, the second one is taking the position of the second carbon. Same compound. One chlorine, one chlorine, one bromine, one chlorine, one bromine, but on different positions. That is positional isomerism. So you can change the position of your functional group. In this compound now, I have the functional group. I have bromine as a functional group, I have chlorine also as a functional group. So when you're changing the position of a functional group or of functional groups in an organic compound, what you form is positional isomer. Okay, so I'm still drawing. So I'll write again 1, 2, 3, 4, carbon to carbon. Yes, I can still have it. Let me have bromine first now. Br. I think I need to slide my pen a bit towards the left so I can have more space. So 1, 2, 4. So I can have, okay, I had chlorine here before. Now let me change their position. So bromine takes first position, while chlorine takes second position. This is another possibility. See that? Then I can draw again 1, 2, 3, 4. Let's say bromine is still taking the first position. Now chlorine from second position is shifting to the third. I can even shift this chlorine to the fourth position. So let me draw again. So I have bromine and then chlorine shifting to the fourth. Okay. Now let me say something. From your understanding of probability in math, this is possible because I have similar things. I have chlorine and bromine. Okay. So I can swap their position. So there's possibility for this bromine and chlorine being on the second and fourth carbon. Okay, I can swap the position. The same thing also goes for the first and the third. I can also swap the position. I can bring the bromine to the third and chlorine to the first. It will be different. Okay. But now, is there any possibility for this? Bromine on the first position and chlorine on the fourth position. What if I swap? You realize that it's still the same thing. Okay, so there is no other probability for this. This is just the same thing. So if I bring the bromine down here and then I take the chlorine to the next one, it's still the same thing. In the sense that you now check which one is more electronegative out of chlorine and bromine, and then you start naming your carbon from that. Okay, or you start numbering your carbon from that. In this case now, the most electronegative is chlorine. So this is my first carbon, this is my second carbon, this is my third, this is my fourth. If I swap the position, bring chlorine here and take bromine down here. If I want to consider where to start naming from, the most electronegative is still chlorine. I'll start naming from or I'll start numbering from the chlorine. So this is going to be the first one, second one, third one, and fourth one. So it's still going to be chlorine being in the first position and bromine being in the last position. So please take note of such things as well. Okay. So you can't say when they are both when your functional group similar ones. Okay, when your functional group are at both ends of the carbon chain, you can't swap their position. Okay, but if they are not at the ending carbon chain, the ends of the carbon chain, you can always swap their position. If one is not on the last chain, the other one is on the end chain, or the ending carbon, the other one is not on the ending carbon, you can always swap the position. Otherwise, do not swap the position. Okay, so what else can I do here? Okay, so I've had them in different positions. Now I can also position them just like I had at first, positioning them in. Have I tried that? Yes, I position them in the same on the same carbon atom. I can also have more probability or more possibility for that. They are both on the first carbon atom. They can both be on the second carbon atom. They can both, okay, if I'm putting them here, it's as good as on the second carbon atom. So they can both be on the first carbon atom and they can also be on the second carbon atom. So I'm drawing for the second carbon atom. I'm putting the two of them on the second carbon atom, Cl and Cl. These are the other possibilities. Okay. So have I seen, oh, there is one possibility I talked about, but I think so I can solve the position. I can solve chlorine itself or bromine. Okay, so that's another. Okay, so now with this, because we have four carbon here, You can also branch off your carbon as well. So I can draw more branching off my carbon atom, reduce it to 3, having my bromine and chlorine on the same carbon, then then I can have trans carbon. This is another isomer for that. So you can also bring this chlorine atom, bring it to the second carbon, leave this one on this. Okay, you can swap the chlorine on the second carbon with the last one, and then you can also change position. You can bring the chlorine and the bromine to the two extreme ends of it. So you can just draw as many isomers here as possible based on position. Okay, so I finished the position isomer already, but I'm trying to see branching. So you can branch off the isomer as well, and then you start changing the position of your functional group. You can even, oh, you can stop the position of the side branch, because if you're stopping the position of the side branch, it's going to form the longest carbon chain. So you can always vary the position of the bromine and the chlorine across these three carbon atoms and draw more isomers for this compound. Okay. So moving on to the next slide, I think that should be the activity slide. Okay. So in this activity, I am expected to draw the isomers of the on the Okay, so draw the chain isomers of C6H11 Br2 C. This is going to be a lot, okay? So I'm going to draw some of them. You're going to try to draw more yourself. And of course, for your exam, I think you are required to be able to draw up to this. No, you are required to be able to draw up to C4. So the example I showed you the other time, yes, you're required to draw up to that. But I think I can just challenge you with the C6H11 Br2Cl. Okay, so I'm just challenging this. But again, for your exam, the requirement is for you to be able to draw up C4 and then with other substituted hydrogen atoms. Okay, so we can draw C4, H, maybe Br2 or Cl, Br, and all of that, just like I have in the first example. That's the hardest. Okay, that's the most difficult you can have. So you can practice that. I didn't complete it. I just explained other ones that you can have for that. But you can try to complete yourself based on my explanation. So this one, I'll just start it off and then you can draw the rest because I still have other things to touch on. All right, so draw the chain isomers of C6H11 Br2Cl. So I have 6 carbon, 2, 3, 4, 5, and 6. Okay, so Br2Cl, I can have, is it possible to have all of them? Yes, on the first carbon. Yes, it is possible. I can have Cl here and have the Br. So then I can start shifting the position of the bromine, the chlorine. It's always good to do it one step at a time. Okay, don't model the whole thing of 1, 2, 3, 4, 5, 6. Let me deal with the functional groups first. Let me see all possibilities for the functional group. Then before I now start breaking off my carbon chain and then start branching my carbon. So I have Cl here, I have Br, I can bring the second and see this. So I've changed the position of this bromine, okay? I can draw another one to bring the position of this same bromine. I can bring it here, okay? What if I move it again? I can also move it here, okay? I can also move it here, keeping the other ones constant in their position. Then I can move it here. So see, you have 1, 2, 3, 4 more possibilities, okay? So keeping these two constant. Now, having done that, I can now start moving any of these two as well. I can start moving my fluorine again, leave this one where it is, leave other ones where they are, and then keep moving this fluorine. Second, third, fourth, fifth, sixth. When I'm done with that, I can leave the two of them where they are, and then I start moving this one again until I see, okay, it is similar to what I've done before and all of that. So that's how to do it. When you are done with all of the movements, changing the position of the functional group, chlorine, bromine, and all of that, then you can also start branching off your carbon atom. Okay, so I think that's what we can do. We can talk more on this in class. Okay, we can sort out this example more in class. Okay, because we have enough time. I think we would have covered the most important things then, so we can check this together. You try to solve and then bring it to class to discuss more about it in class. Okay. So yes, before I end or before I move away from isomerism, I have another one, functional group isomerism. Oh no, I'm not meant to do functional group isomerism. It's not required for unit one. Okay, so it's position isomerism we have really fun. But I'll just quickly talk about this and then, of course, not required, like I said. So you don't need to really bother yourself about it, okay? But just because I have it in the exercise, let me just touch on it quickly. So I have this compound, sorry, this compound C2H6. Oh, C2H6. C2H6 already is complete. I think it is C2. Okay, yeah, I think. Now, I can have this as CH3, CH2, that is 5 hydrogen, then OH. Yes. This is a functional alcohol, right? That molecular formula can give you the structural formula. CH3, CH2, OH, and alcohol. This is ethanol because you have two carbon atoms. So this is ethanol. Then the same functional group, the same molecular formula can give you CH3. Okay? This CH2, I can add the hydrogen and then bring the oxygen in between. Add the hydrogen shape from the shape. This is an ether. This is methyl methoxide. Okay, methyl methoxide. Okay, so you have two different functional groups here. You have alcohol here. Here you have the ether or the alkyl alkoxide. What am I trying to write? Ether. Yeah, the functional group. Okay, this is the functional group. Okay, so the functional group here is ether. The functional group here is ethanol. So you can have the same molecular formula having two different kinds of organic compounds entirely, not just in naming. Their characteristics will be so different because they have different functional. So touch more on this in unit two. Okay, we'll go more on stereoisomerism and functional isomerism in unit two of your textbook. Okay, so let's see. I think I've come to the end of it for today. Other than the fact that might need to solve questions from the textbook. Yes, when we meet in class or tomorrow. So that's all I have for today. So I'm going to see you guys.